All right, for those of you joining by video, this is the second hour of our class. This is also a refresher. This is 1.8. And it's on exponential and logarithmic functions. So we're going to say if b is greater than 0 and b does not equal 1, the function f of x equals b to the x. It has a domain of all real numbers. Negative infinity to infinity. And the range is 0 to infinity, not including 0. And we could do a quick table of that, looking at what we've got. We've got x, we've got y equals b to the x. Let's just do -1, 0, and 1. It ends up being b to the -1, which is 1 over b. B to the 0, which is 1. And b to the 1, which is b. So that's 1, we'll say that's b, that's 1 over b. And we plot those points. Does some shit like that. And to the left, it goes along the x-axis. The x-axis ends up being an asymptote. So negative b to the x would be downward. Just reflected over the x-axis. And if you have y equals b to the negative x, it actually reflects across the y-axis.
So if it's a negative on the value y is equal to, then it's reflected across the y. But then if it's a negative on the exponent, it's
If it's a negative on the exponent, it's reflected across y, which is that
Okay.
axis. If it's the y, if the value is negative, so like no matter what we do, the answer ends up being negative because this was positive, so it flips it over the x.
x.
And so if we had something like f of x equals 2 minus 3 to the x. This is gonna looks like -3 to the x. Shifted up 2. So negative 3 to the x would be like this. That's negative 3 to the x. So if we shift it up to 2, my asymptote moves up there. My intercept moves up 2. And it looks like that. So that would be 2 minus 3 to the x. And I'm betting throughout all of algebra, you like e to the x the least. You guys remember e to the x? When you did exponents, e to the x was probably your least favorite. It's pretty much probably your first introduction to e. By the end of the semester, e to the x is gonna be your favorite fucking function. Better than y equals x, which is super. You shake your head no, it will be. It's glorious. I'm not getting this shut up. So, if we do look at e to the x, e to the x has the same graph, but as I was saying, y equals e to the x is gonna be your best friend. Your BFF.
Is this e to the x just the one that increases on what the asymptote of the x-axis?
It looks just like b to the x, but b equals e. So and e is approximately 2.71. I can actually give you a definition for e. You've never seen e defined before, I'm betting. E is the limit as x goes to infinity of 1 plus 1 over x to the x. That's fucking magic. I can give you a few more decimal places, 2.718282. I don't know if it keeps repeating. Kind of looks like it does.
Weirdly enough, I think we've only touched on it and like, at least in Mr. Blake's algebra class, only once. That's kind of it.
Yeah, you only really do it in like the exponential sections in algebra.
The only place to stop was philosophy.
No, this is gonna end up being the good shit. You'll see. You don't believe me. But you will see. Logarithms are the inverses of exponentials. So b to the x and log base b to the x are inverses. E to the x and log base e to the x are inverses. But when we have log base e, we write ln instead of log. It's a good idea to put the thing that's inside the logarithm in parentheses. Just in case you have something added or subtracted to it and it's not in it, it makes it clear.
Log E is just N.
What?
Log E is just Ln.
Ln, yeah, it stands for natural log. Ln, it looks like an I, but it's L, stands for natural log. And maybe I'll point out if you have 10 to the x and log base 10 to the x, This just shows up as log x. Base 10 isn't shown. So y equals log base b to the x can be rewritten. This is not an inverse thing, but rewritten as b to the y equals x. And so since they're inverses, that there should flips for domain and range. Domain log base b is the range of b to the x. And that was 0 to infinity. The range of log base b to the x is the domain of b to the x, which is negative infinity to infinity. Where our asymptote used to be the x-axis, now the asymptote's the y-axis. Boom. And where we used to worry about where it crossed y equals 1, we're worried about where it crosses x equals 1. This goes like this and like that. That is y equals log b to the x. If we do y or y equals negative log b to the x. This is taking all the values and making them negative, which flips this graph upside down. Yeah. And when we have y equals log base b of negative x, that's where it flips across the y-axis. And I'll do some shit like that. Does he still do that?
Yeah.
It's fucking great.
I had what, two semesters ago, I think, yeah. So does that.
I had him for trig over summer for a 4-week, like I took trig the first session and then. Back then we had a separate class called pre-calculus, which was after trig. And I took pre-calc the second one, so it was like. 2 semesters of math in 8 weeks, it was a fucking crash course. But I had Blakely the first one and within just a couple of days, students were whining about too much work and like, you know, that's kind of fucking. You could condense an entire semester down into 4 fucking weeks. You gotta work fast. But they would, and so he started doing that, simulating a student whine. Oh my god, it cracked me up.
You get a lot of. Like, so that you get a lot of homework, even on the regular cycle.
It's good for you. students don't think that, but like. The more you do, the better you are at it, like doing enough to understand it, you understood it while you're doing it. But if you keep doing more problems than just like, oh, I think I get it, and you do like fucking 5 or 10 more. Then like you're gonna lock it in a little bit better, rather than just getting it right then. And depending on what class you take. Some classes, like if you took them for algebra problems don't take that fucking long to do, a lot of them don't. So you can assign a lot of homework in algebra and really not eat up a lot of the students' time next work. Unless they're just not getting it. Alright, more on logarithms, let's do properties of logs. This had an expansive list of shit. Again, we're going to assume b is greater than 0, b does not equal 1. We're also gonna say a is greater than 0 and c is greater than 0. And r is a real number. Rule, I'll say a log base b of a times c equals log base b of a plus log base b of c. Then we have the division one. Log base b of a over c is something similar, but it turns into subtraction. And if you took this with the right professor, a lot of professors will show you how this works, why these are true. You base it off from y equals log b of x, you rewrite it as b to the y equals x, you can show it that way. Then we'll have one of the fun ones, one of the more useful ones. These are both useful, but this one is glorious. We have it on the inside, log base b of a to the r is the same thing as r times log base b of a. In the same line, but we tend to write it differently because students forget. We have 1 over a like that. 1 over a is like doing a to the negative 1. And so it really is just a play, like a specification of c. We put the negative 1 out front, it makes it negative log b to the a. The change of base formula, that's what it's called. Change of base. Log base b of a equals log a over log b. Or we do ln of a over ln of b. We can actually choose any base we want there, but they have to be the same bases on both. And as I mentioned earlier, y equals b to the x. We can rewrite this as log base b of y equals x. I think I wrote this earlier as x equals b to the y. It's the same thing as log base b of x equals y. So depending on where the exponent is, they swap like that. You guys ready for some examples to work through? Does anyone need this page up longer? Okay. Anybody else need that longer? Alright. So in the following things, we're gonna solve. For x. And this one will say log of x equals 3. So this is really the same thing as log base 10 of x equals 3. We have no law of no bases written, base is 10. Now, one way to do this is rewrite where this is the base. This is the exponent. And that's the other side. So x equals 10 to the third power. So x equals 1000. Another way of doing this is recognizing this, rewriting it with the log 10 of x equals 3. And then treat. This is the option. Treat both as exponents on a base b, whatever it is, in this case 10. So treat this as 10 to the log 10 of x equals 10 to the 3. I know that I had that all written down. I did not. This is related to the inverse functions. B to the log b of x equals x. And log b of b to the x equals x. That's related to inverse functions, inverse function properties. When you stick one of them in the other, that's what you get. So that's why we raise it to both sides to the power of that. The 10 log 10 cancel, we just get x equals 10 to the third, which is 1000. We're really treating this, we're sticking that in for the x. Here, we're sticking that in for the argument. This one you can see, you pull the x out, like on one of our property rules, the x comes out. And log base b of b equals 1. Those are actually some good ones now. Log b of b equals 1. Log b of 1 equals 0. Those are two good ones to know. So we'll do another one. Let's say natural log of 2x minus 3 equals 2. Hopefully you don't write this step, you get used to doing it without, but this is the same thing as writing log e of 2x minus 3 equals 2, just as a reminder. We can do what we did before, base and exponent. sorry, base. And exponent. So 2x minus 3 equals e to the 2. And the other way to get here is treating both sides as exponents of e. E to the ln cancels and you get 2x minus 3 equals e squared. Both of them will get you there. And you're solving for x. We add 3 to both sides and divide by 2 or multiply by 1/2. We have x equals 1/2 times 3 plus e squared. For another. Let's just bust through some of the algebra of it. 3 to the x equals 7. One approach is doing the rewrite method. That's our base. That's the argument. So x equals log base 3 of 7. The other way of doing this is taking log of the same base on both sides, using the base of the exponent. Oops. And the log base b of b cancels out. This is x equals log 3 of 7. That's an exact answer. If you need the actual value, like you're doing some engineering or shit like that, you need to rewrite this as either log 7 over log 3 or ln of 7 over ln of 3, because these two options have calculator options. There's no calculator. A lot of calculators don't have a calculator option for this. If you're lucky, your calculator, if you got an expensive calculator, it does. But just knowing to change your base formula, a simple calculator does this pretty quickly. This is gonna be fun. E to the x minus e to the negative x over 2 equals 1. Not yet, we don't want to do that. We do want to fractions, so fuck fractions, right? So if we say fuck off to fractions. And believe it or not, we still technically have a fraction. Because e to the negative x is 1 over e to the x. So here I multiplied both sides by 2. Here, I'm gonna multiply both sides by e to the x. And e to the x times e to the x is e to the 2x. Or another way of looking at that is e to the x squared. Which you might find helpful during the next step. I'm gonna move the two e to the x over by subtraction to the left side. And if I look at e to the two x as e to the x squared. You might be able to notice that if I say u equals e to the x. This is u squared minus two u minus one equals 0.
Doesn't e to the x equal u? Or is it?
Well, I'm
no, we
defining
just have
it, I'm doing just a
Just this
substitution,
time, okay,
just a regular substitution. And we like to use u a lot because u goes unused for most things, so. Now, this doesn't factor, so we gotta do quadratic formula, so as a reminder. It's negative b plus or minus square root of b squared minus four ac over two a. If we apply that here, it's positive two plus or minus negative two squared minus four times one times negative one all over two times one. U equals two plus or minus. The inside of that is four plus four or square root of 8. Square root of 8 is square root of 4 times square root of 2. So I could also say this is 2 plus or minus 2 root 2 over 2. And this all cleans up to 1 plus or minus the square root of 2. We didn't start with u though, so we can't end with u. We gotta do our sub back in. E to the x equals 1 plus or minus the square root of 2. One of these doesn't work. The range on e to the x is greater than or equal to 0. But square root of 2 is approximately 1.4. If I do 1 minus 1.4, I end up with a negative number. So the negative one is actually out. We can only do 1 plus square root of 2. And if you want x, you can just take the natural log of both sides. And ln and e cancel out, the x comes down. X equals natural log of 1 plus square root of 2. That's an exact answer. If you need a decimal number for whatever you're using, like some engineering thing, grab a calculator. I think you haven't got to see enough limits today. So maybe we should do some limit problems in our last 10 minutes. This is good shit. There you go, Tyler. Smile. Eat it up. You're gonna love it. Does anyone need this out longer? Speak now or wait for it to be scanned. All right. So we're gonna look at find the limit. As x goes to infinity. Of e to the x plus 1 over e to the x minus 1. It's always worth Try and plug in, try x equals infinity. We get e to the infinity plus 1 over e to the infinity minus 1. And e to the infinity is just infinity, this ends up being infinity over infinity, so this is bad juju shit, we don't like this one. So the way we address this. Is we're gonna multiply by the reciprocal of e to the x. Multiply top and bottom by 1 over e to the x. And if you do that. We know e to the x never equals 0, so this is a valid operation. E to the x, and you're distributing it to both of them. On top and bottom. This becomes 1 plus 1 over e to the x. And 1 minus 1 over e to the x. Now, when we try x equals infinity. We get 1 plus 1 over infinity. 1 minus 1 over infinity. And hopefully, if you've been practicing your homework, you recognize 1 over infinity as what? 0. So we got 1 over 1, it's just 1.
You have to get rid of e over x as a whole. And turn it into 1 over e to the x, and then we can plug in infinity. That's what works better.
Yeah, like this is an indeterminate form, we will. When we learn the rule called L'Hopital's rule, we need to know derivatives first. There is an easier way to do this. But. Understanding why it works, like this, it's based on doing shit like this. We're a long ways from L'Hopital though. So what about limit as x goes to negative infinity? At e to the x plus 1. Over e to the x minus 1.
Same thing.
Right? What happens if I plug it in? We get e to the negative infinity plus 1 over e to the negative infinity minus 1. It kind of looks the same, right? It is not the same. What does a negative exponent mean? It means this is 1 over e to the infinity. Plus 1 over 1 over e to the infinity. Minus 1. If we deal with negative exponent, it just shifts to the denominator. Hopefully you guys remember that from exponents. 5 to the negative 2 is the same thing as 1 over 5 squared. Sidebar there. But now, this just works just fine. 0, 0. Got 1 over negative 1 is negative 1. Now, there is one that doesn't work with negative infinity. At first glance. If we do limit as x goes to negative infinity. And we have like 1 plus 1 over e to the x. And 1 minus 1 over e to the x. Or if it said like limit as x goes to negative infinity. 1 plus e to the negative x and 1 minus e to the negative x, these are the same thing. When you evaluate at infinite negative infinity, should be negative infinity on both. When you evaluate at negative infinity, you get the infinity over infinity situation. But here the problem is the 1 over e to the x. So we're gonna multiply by the reciprocal. Just multiply the top and bottom by e to the x over one. That's a valid observation, that's never zero. And we get e to the x plus one over e to the x minus one. And now we're back to that one up there. And we just saw that equal -1. Some classes, everything we've done is taught in pre-calc so far. All the limits and shit like that. On Wednesday, we start. Or Thursday, we start the real shit. This is where we start getting good. Chapter 2 is on derivatives. I'm done, so you are free to get the fuck out, or have a nice day, or stay and ask questions, whatever you'd like to do. And I will see you guys Thursday. Have a good day.